So we talked about neural networks last time, right? So we talked about what they are. Every single neuron is, in that one was a basic linear classifier. But then we replaced that, perceptron-like activation. We replaced that one with a normal neuron, so we just added one activation. So one neural network looks like this. So you have a bunch of inputs. It has multi-dimensional input. And then we basically do process it with those neurons. So neurons are the basic units which can do computation. Again, every single neuron is basically one linear classifier. So you're going to get whatever input is, computes a bunch of, it computes one linear combination of them, and then after that, it's going to activate it, right? So by activation, it means that it passes through one nonlinear function. So what is crucial in neural network? What is the most important thing we need to have necessarily for the neural network to work? The nonlinearity, which was being imposed by the activation function, right? So if you don't use any activation, it's really, we talked about it last time. It's going to get back to a normal linear model, which you have seen that for many problems, it's not going to work properly. So we talked about this guy, and then we talked about its expressive power. Basically, we talked about this idea, if you want to just represent a class of functions, how powerful the neural networks are. And we started with the binary functions. If you remember, for binary functions, we had this specific nice feature that we could count the number of possible functions. And then we wanted to just be able to represent all of them. We just discussed how many neurons we need. If we want to have one neural network with only one hidden layer, which we called it a shallow neural network, how does the number of neurons in that hidden layer scale with the number of inputs? Do you remember? So if I want to represent one binary function, and this binary function has d different inputs, okay? D different binary inputs, and I want to represent it with only one hidden layer, one shallow neural network. How many neurons do I need in this neural network in the hidden layer? I don't want the number exactly. How does it scale with the number of inputs? Is it linear? Is it exponential, right? So when you have d different inputs, you need something in the order of 2 to the power d neurons. And we said this is a huge number. Like if you have a very big input, then you need exponentially large number of neurons. It is not feasible. But deep neural network had this key property that when we go deep, we are going to just significantly reduce in the number of neurons that we need. So now if I go as deep as logarithm of the number of inputs, how does the number of neurons in total scale now? It's going to be log d is the number of layers, right? But forget about it. If I make it deep enough, how can I drop the number of neurons that I need? Would it be still exponential? No. What would it be? How does it scale? Do you remember? Linear, right? We can make it as efficient as linear increase in the number of neurons that we need if we make it deep enough. So if you have enough number of layers, then you essentially need linear number of neurons. We talked about it as well, that the number of layers that you need to make is essentially proportional to the logarithm of input, which made us this conclusion. If we just go deep, the deeper we go, our power is just exponentially increasing. Meaning that our model, as we go deeper and deeper, is going to be exponentially more powerful in representing different functions. We talked about this, that this kind of problem, you can simply project it into any classification or regression problem. So if you have any classification problem, at the end of the day, it's like representing one binary function, which you can do it with enough number of neurons. And this enough number of neurons should be only linear when you have a deep neural network. Same thing happens for a regression problem. Again, regression problem can be approximated by a classification problem, and then that approximation can be represented by a neural network, which again, if you have a dip enough, then your power is going to exponentially increase. Moral of the story, neural networks are, especially the deep version of them, are very sophisticated models that can represent any sort of function that we want. And then the last question we left last session with was, what was the last question? How to train the neural networks, right? And what do I mean by training? Any idea? What do I need to find when I'm doing the training? Weights. Great, right? So these neural networks, all of them have weighted inputs, right? When they want to compute their output, they have a bunch of weights which they can play with, right? And the kind of function that you can represent is based on those weights, right? When you change the weights, the function is going to change. Now you want to see how you can find the right weights so that you can do the representation that you want. So this is the problem that we try hard today to explain. And you're going to see that this is actually very, you can develop some algorithmic approaches which can simply just, based on gradient descent algorithm we talked about before, it can simply do the job for us. And this is basically what we are now, right? Nowadays, we pretty much do anything with these deep neural networks. So we are going to understand a bit of inference by neural networks, how we can use one neural network when it comes to practice, if we really want to do classification by neural network, how we can do it. And then we're going to talk about the training problem, and specifically we are going to talk about the backpropagation algorithm. This is the key algorithm which enables us to do the training, because it's going to help us compute efficiently the gradient with respect to all the weights in the neural network that we want. And this is basically what we need if we want to do gradient descent, right? In every single iteration, we need to get our weights, and then we need to just move in the direction, opposite direction of the gradient. And then once we understood these two parts, then we are going to complete the training evaluation loop, which basically give you this, this idea how you can use, for instance, PyTorch or TensorFlow or any other platform to just implement one neural network and train it based on the data you have. So, any question from previous session? Everybody's cool with neural networks, right? Great. So if everybody's cool with neural networks, let's first take this neural network and put it into a box. So what do I mean by putting it into a box? So here, see what is happening. So this is your neural network. We talked about this, that we have one input layer, we have a bunch of hidden layer, and we have the output layer, right? What is the input layer here? What is the input layer? The very first one on the left side, which includes all of those x's, right? So what is x1 to xd? It's basically the d-dimensional input that you have, okay? So you have a d-dimensional input. It means that, for instance, you had one image. The image is image of a cat or dog, and then this has d different pixels in it, right? And then you put those pixels next to each other as a kind of vector. And now you can fit it through this input layer to your network. And now here you have two hidden layers, the green layers that you see here. And the final layer is the output layer, which you take the value that it computes, and based on that, you infer what is inside that image, right? So this is basically the same thing we did when we were doing linear classification, but in that scenario, we had only single neuron, right? Every single input was directly connected to all the lengths of the red neuron at the output. Now we have a lot more, right? Now, one question, what is the depth of this neural network? It's 3, right? So the depth is 3. Is it a deep neural network or not? It's a deep neural network because it has more than one hidden layer, right? Okay, great. Now, every single neuron has a bunch of weights, has also a bias potentially, so it means that every single input connected to that neuron is being multiplied with some weight, which we can freely choose. and there is a bias dedicated to that neuron, again, we can freely choose, right? And now what I want to do, I want to look at this whole thing again as a model. So if you remember when we started with supervised learning, we said we have a data set, we have a model which is potentially parameterized, right? A bunch of parameters it has. And then we have a training algorithm or learning algorithm. This is going to look at the data set, look at the model, and tries to find the right parameters for that model. So if I want to interpret this guy as a model, I can simply put every neuron in between inside a box, right? So I can think as a black box. So you really know what is happening inside, but when you want to just look at it from an abstract point of view, you can think of it to be one box, right? And then this box is essentially one function, right? So it gets a bunch of inputs, x1 to xd, one d-dimensional input. It's going to pass these values through a bunch of operations. We don't care what is there. But then at the output, we are going to get y, the output of the neural network, the value that the output layer is computing for us, right? Now, this model is parameterized by w. What is that w here? Can you tell me? What does it include? It includes weights and biases, right? So the weights and biases of every single neuron you have inside this neural network, you can write it down in form of a list, and that list is going to be your weight list, W, right? So that W is potentially very, very large, right? If your network has a huge number of neurons, then that guy could be potentially very large, right? It could be a very long list, including the weights of the first, second, and so on till the last neuron inside your neural network. If they have biases, the biases are also included. Everybody's cool? So it's true that the computation inside is quite complicated, but we can look at everything in this form. And then again, we can get back to our supervised learning problem as before, right? So in supervised learning, we have a bunch of data samples. So these data samples are x's. So here x's are basically the d-dimensional points that I showed in this diagram here. So every single input is one of those xn's, one of the samples that I have. And the output is one label v, right? So this label could be a label of classification. It could be a value when we are talking about regression problem. And essentially what we want to do, we want to tune one model. So we want to get this model fw such that this model is somehow, when it looks at xn, it's going to give us the right or approximately a right label, right? So this is again the same problem, but now our model is actually set by the neural network, right? So that fw is essentially our neural network, the model that we had here. So fw is this guy, and those w's, we do know what they are. They are weights, or what we call them model parameters. Let's say we have m different weights in total. So we're going to have a vector of length m, a list of length m, that is our w. And essentially, our hypothesis set is specified by that neural network, right? So we assume that our input is connected to the output by a function which can be represented by this neural network. Is it necessarily correct? No. This is again an assumption, right? Exactly like the linear classification or regression that we did, right? In linear regression or classification, you think that your input and output are connected by a linear function, right? But it turns out that is not always the case. No problem. I mean, we approximate it. Same thing happens here. Again, you have a neural network. You assume that it is able to represent that function. Whether it's true or not, you cannot say because the problem is very complicated. But you assume that at least it gives you a good approximation. Yeah? And what you wish for is that you find that right approximation. So, now, if I set my model to be the neural network, and I have the data set, the last thing left is to do the whole learning process, right? So we need to develop one learning algorithm, and that learning algorithm is going to essentially find us the right model inside our hypothesis set, right? So what does it mean, the right model now? What does specify the right model for us with a neural network? No, we are going to minimize the loss, but what is the right model? If I want to just specify one model, what should I specify? The weights, right? So maybe I made the question complicated. No, it's not complicated. So I need to specify the weights, right? At the end of the day, I am going to search for the right choice of weights, correct? So the learning algorithm that we want for a learning algorithm to get the data set, somehow deal with this neural network, plays around with this neural network, and ends us with a bunch of optimal weights that are set for that neural network. This process, this is what we usually call it in the domain of deep learning. We call it training. Yeah? We somehow used it before as well when we were dealing with the other algorithms. I mean, the process of finding the right weights is essentially what we call it training, because we somehow feel like the neural network is like a human being or a creature that we are just giving the data, and it tries to find out, it gets trained to somehow mimic the behavior of that data set. Okay? This is the idea of training. This is what we are going to do next. Now, before we start with doing the training, which is the main topic of today, let us first see how we can, say for instance, we have one neural network and somebody told us that I have already done the training for you. Okay, so the neural network is perfectly trained. Now how you can use it. This is the idea that we call it inference, meaning that when I have a neural network, when I give the input, when I give the image pixels into this neural network, I'm going to see some outputs at the output layer of this neural network. How can I infer from those values, for instance, what the image is, right? This is the idea of inference. And how can we do this? Well, if we have a classification problem, and if our classification is a K-class classification, we can essentially make our neural network to give us one of the values, class 1, class 2, class K, at the output, right? Meaning that we can put that activation function at the very output to somehow look at one real number computed, and out of that it gives us K different discrete numbers. But based on our experience up to this point, do you think this is a good idea? If you remember when we started with binary classification, did you think that when we wanted to do the training or we wanted to find the optimal weights, was it a good idea to think about like a step function at the output, so we just classify very harshly at the output? No, we use logistic regression, right? We use sigmoid function, we computed some soft value, and out of that soft value we computed the loss and tried to minimize it. This was the logistic regression idea, and we talked about this, that if we do this one, we are going to benefit when we use the gradient descent, because now we're going to have gradients, right? It's not like the step function that does not have a gradient. This is the same thing here as well, so we're not going to do this hard thresholding here. The better idea is to always interpret the output of the neural network as probabilities, right? And we talked about this before, but let's once again look at it on the neural network to see how we can do it. So let's say I want to do binary classification. And if I want to do binary classification, I am going to put my output layer to contain only one single neuron. Okay? The output layer has only one single neuron, meaning that the output of this neural network is it a vector or a number? Is a scalar, is a number, is a single number, right? So I am going to get the image, for instance, this is the image of a dog, and then I present it in form of a d-dimensional vector, so I put all the pixels next to each other, and I pass it through my neural network, right? So this is going to get processed on the neural network, so a bunch of values being computed at every single neuron, and then finally at the very output layer, very last hidden layer, you're going to have a bunch of values We used to call them the embedding when we were working with the SVM. It's the same thing, right? The bunch of features in the very last hidden layer, which are represented by phi vector. And then you're going to compute one linear transform of that phi at your output layer. And you want to decide based on that value what that image is, right? Yeah.
How do you represent an image in such a way that a neural network understands it?
So you have an image of, for instance, 8-bit pixels, 8-bit pixels, right? 8-bit image. It means that it's, say it's MNIS, okay? MNIS is 28 by 28, so it's going to be 784, right? 784 different pixels, right? Now, every single pixel here is 8-bit number, 8-bit digit. An 8-bit digit could be either 0, 1, till 255, right? So every single of them is one of those numbers, right? So you can either make, I mean, the most naive approach is you make one vector, is 784 entries long, and then every single number there is the corresponding pixel. Okay? And then you feed it to your neural network. Better idea, you get this vector that I told you, divide everything with 256. Then you have a bunch of numbers between 0 and 1, right? This is again representing your image.
Right. In 256, that's just every possible color, isn't it? It's like RGB value.
It's not RGB value. It's actually gray value. If you have RGB, then you have 3 channels, right? Oh, yeah. Every single of them is in that form.
Right. So you're just classifying it as over black and white then.
Yeah, you can think of it. I mean, if this is RGB, then you could have your first channel, second channel, third channel. At the end of the day, you can make it a huge vector, right? Yeah, but I mean, we are dealing with fully connected networks today. I mean, at the very end, we're going to discuss how we can expand it to the convolutional neural networks as well. But for image processing, I mean, these are not, I mean, you can do it, definitely, and it's going to work, but this is not the best choice. I mean, of course, if you go for convolution, that's going to be even more efficient. But at the end of the day, it's again the same thing. I mean, it's just again doing linear operation and activating it over and over. Okay? Everybody's cool? Okay. So now I have my image. I represent it in form of a vector, and then I pass it through my neural network. I'm going to compute the features in the first hidden layer, second hidden layer. I get to the last hidden layer. I have a bunch of features. And then I get those features, I pass it through the last neuron, right? And the last neuron is going to just linearly combine them with its own weights, and then finally compute one activation function on that, right? Okay. The output of that one, we talked about it before. The best way of dealing with it is to just make the output to look like a probability, right? And then we interpret it as the chance of that image belonging to one class. For instance, we can compute one activation of whatever we calculated in the output neuron, and then out of that value, we would say, okay, this is the probability of the image belonging to the class dog. And of course, the probability of image belonging to class cat is 1 minus that thing, right? And now if that probability is more than half, then it means that this image with higher probability would be the dog image, so I'm going to call it dog. So say I have computed the probabilities. These bars that you see here, dog probability is higher, cat probability is lower, so I'm going to give it the chance to be dog, right? So this process, starting from the image at the input, computing the output y, interpreting that output y to be something meaningful, and out of that, inferring the class of the input image, this whole thing is what I call it inference. Okay? Everybody's clear? Now, if I want to do this inference, what should I put as the activation function at the output layer? How did we do it in logistic regression? What did we put at the output? Sigmoid function, exactly. And what was the property of sigmoid function? It's always between 0 and 1, right? It always computes a probability for you, right? So meaning that the output of your neural network now looks like a probability, right? So this is the thing that you should always keep in mind. So whenever you design a neural network for any task, no matter it is classification or regression, you first need to understand how you want to interpret the output of this neural network, and you need to design your neural network to somehow show that kind of behavior, right? For instance, in this case, as we said, we can just put the output layer, output neuron, to be activated by sigmoid function, and then essentially we compute a sigmoid activated output out of these features that we have in the last hidden layer. Essentially, we compute W times H. I should have put one transpose here as well, I think, but I forgot. That's okay. But at the very output, so this is the output neuron. Now I am computing Y. So essentially, I'm going to get the different features I computed in the last hidden layer. Say I have phi 1, phi 2, till, for instance, phi, I don't know, T. Then every single guy here has a weight. So to compute Y, I first compute a Z value. That Z value is going to be the summation of every single W times the corresponding phi, and then this T can run from 1 to T, and then I add potentially one bias to it. This is the linear combination. These are the weights of my neuron. This is the bias of the neuron, and at the end I set Y to be the sigmoid activated of Z, which is going to be something between 0 and 1, right? And this guy is between 0 and 1. I'm going to interpret this guy as the probability of my image belonging to the class dog. Now, the output of my neural network, so this neural network I'm showing with this black box function fwx is going to compute me the probability of belonging to class 1. Of course, I don't need to compute the probability of class 2 anymore because that is going to be 1 minus this guy, right? And once I have this, for inference, each time that I pass a new image through this neural network, I'm going to compute the output of neural network. I do know this is probability. I'm going to take the class which has higher probability, right? Everybody's cool? Questions? No question? Great. So if you got no question, how we can do it for multiple classes if I want to just do multi-class classification? Yes, you can. We can use softmax, exactly. So you remember when we were talking about classification with cross entropy? Remember that? When we just did maximum likelihood and then we ended up with one loss function which we called it cross entropy. And I put something in the appendix. Anyone had the chance to check the appendix? No chance? Okay, so there in the appendix we had softmax, and today we are going to explain it. So what we can do here, again, say we have k different classes, okay? More than 2. K different classes. No, we cannot simply compute the probability of one class because, well, we need to just make the probabilities work together, right? So the image could be from class 1 or 2 or 3 and so on, right? So you want to have a sort of probability distribution over the whole classes. The way that you can do it is to just compute k-dimensional output. y1, y2, y3 till yk, right? And you want these values to represent the probability of your input belonging to every single class, right? So meaning that every single of them, every single entry inside this k-dimensional vector should be a number in which range? 0 and 1, because they are probabilities, right? But this is not the only property they need to satisfy. There is another property. What is that? Add to 1, right. So they need to add up to 1 as well, right? Because they are probabilities. Like you cannot have the probability of cat being 1 and dog being 1 as well, right? So if cat is the probability of cat is 1, the probability of everybody else should be 0, right? This is the probability distribution, right? So now we need to just make such a thing. So how we can do this? This is the idea of softmax. So we can essentially, now instead of having one single neuron at the output, now we can have one larger model. So what we could have instead of having this one, so we could just get all of these features, phi 1 till phi t, and then we pass them through one linear block W, right? And I can compute y to be W times vector phi plus 1 vector b. Okay? Now, I told you I want this y, this is k-dimensional vector, right? Giving me k different probabilities at the very end of the day. Right now I'm not computing y, I'm computing z. So this is k-dimensional. So if it is k-dimensional, and phi here is t-dimensional, okay? I think t was not the best notation, but anyways, I used it. So this is t-dimensional. So I want to get this t-dimensional guy, and I want to transform it into k-dimensional. What should be the size of this matrix? How does it look like? How many columns does it have? T. How many rows does it have? K, right? So I'm going to get k times t different weights, and then I multiply them to all of the features. I'm going to compute a k-dimensional output, right? If I want to have biases, I can add bias to every single of them as well. What is the dimension of this one? Again, k, right? So k different biases I could have. Now, if I do this computation, I'm going to have that z vector. This is k-dimensional. I get k different numbers. Now what I want to make them between 0 and 1, and at the same time add up to 1, right? And how can I do that? This is the idea of softmax. So I can use softmax. What does softmax do? It's going to get every single z value. So every single z that you have here, at the end of the day here, z is going to look like z1, z2 till zk. Now, when you do softmax, you first take this to exponent. So you're going to compute e to power z1, e to power z2, and so on till e to power zk. So these values are all non-negative, right? They are positive. Actually, they cannot be 0 as well, right? So exponential function, if you take e to any power, it's always going to be positive, right? And now I am going to just divide it by summation of e to power zi, I from 1 to k. Okay? So sum of all of them. Now, what's going to happen if I sum up every single guy inside this vector? What's going to happen? What is the first entry? The first entry here, so this is my y vector. What is y1? y1 plus y2 plus yk. How does it look like? What is y1? Can you tell me? EZ1 divided by that sum, right? Summation of EZI over I, right? What is y2? EZ2 divided by summation of EZI over I, right? I can keep on going till the last guy, right? This summation here, e to power zk. What is this sum? It's 1 because denominator is the same. Nominator, when you add up, is essentially sum of all of those e to power z's. So it's going to add up to 1, right? So you have a bunch of numbers. All of them are non-negative. All of them are between 0 and 1 because denominator here is always larger than every single of them, right? And they add up to 1. They are essentially probability, right? So what does softmax do for you? It gets any real valued vector, and then it just converts it into a probability distribution. Everybody's cool? Now, why do we call it soft max? Which guy has higher probability? If I have the values inside this z vector 3, 2, 1, after converting by softmax, which probability is higher? The first one, the one which computed for 3, right? So softmax is going to essentially give higher probability to those who have larger z values, right? So it's not doing anything weird for you. So once you computed these z values, it's going to say that, okay, the z1 is the largest value, so I'm going to give the highest probability. And maybe the next one is zk, so it's going to be the next highest probability, and so on till the last one, right? But the whole trick is that it's really computing you a probability distribution, right? And this is exactly what you need to have when you want to do classification. So essentially, instead of having a single sigmoid function, you have the softmax plus a linear transform, these two modules, and then out of that you have a probability distribution. Now again, you'll look at the probability distribution, and you're going to take the class which has the highest probability, right? So for instance, if z1 is the largest guy, then after computing the values inside y1 is going to be the highest probability, and out of that you are going to say, well, the class is class 1, right? Everybody's cool? Questions? Sorry? I think it was lecture 4? Yeah, I mean, if you wanted to do maximum likelihood again, then there I introduced softmax for the multi-class classification. Yeah. But no worries, I mean, it's the same thing as we did here. So, questions? No questions? Okay, I'm a bit slow today. So, now, what if we want to do regression? How we can use a neural network to do the regression? Any idea? Do I need to do anything specific at the output, in the output neuron? If I want my output in the regression, we usually are just approximating one function, right? And then if I want that function to give me any real value, should I do any activation in the output layer? Linear activation means no activation, right? So yeah, this is exactly the case. So if you really want to have a real output, you essentially don't need to do any activation in your output layer, right? So you drop that sigmoid, or I don't know, whatever it is, whatever you computed here, so this linear output that you computed here, you exactly copy it on y. So y is going to be exactly your z value, right? So you don't need to activate it if you're happy with any real value. But it's not always the case. I mean, you could essentially do it in one dimension or multiple dimensions. That doesn't change anything. But this is not always the case. Sometimes, for instance, you want to have a real valued function, but you want it to be between two different values, right? A and B, for instance, right? And now, how you can deal with that? Any idea? How should I do at my output layer if I want to do that? I want to restrict, I still want to have a continuous change between A and B, but I want everything to be between A and B. Is there any way that I can restrict my output? If I use sigmoid, I'm going to restrict it between 0 and 1, right? Correct? Now, and can you scale it or shift it to get into whatever you want? Yes, right? So in that case, you potentially could have one nonlinear activation like sigmoid, and then you do a scale and shift. So moral of the story, if you have a real valued output which you're happy to have take any value, you could essentially do no activation, just linear activation, get whatever you compute in the linear transform, and then exactly copy it at the output of your neural network. If you want to keep it in an interval, then you can essentially do some activation any activation that you want, which restricts your output, and then you do scaling and shifting in order to get into the right interval. For instance, here, I want my output to be between -2 and 5, right? So I'm going to compute the sigmoid of the z. So once I compute a z value, here when I get z value, y is going to be sigmoid of z. And that sigmoid activated value is going to be between 0 and 1, right? Now if I multiply it with 7 and then subtract it from 2, then whatever that number, 7y minus 2, whatever that number is something between -2 when y is 0, and y could be at most 1, so it's going to be at most 5. So it's somewhere between -2 and 5. So I can put it in the right interval that I want. Everybody's clear? But then that output is essentially my output, right? So I'm going to compare it to the samples that I have, the label of the samples that I have in the regression problem. Okay, so questions? No question. So everybody's happy now. If I ask you, I don't want you yet to do any training, but if I tell you I want you to just build me one neural network which does this job for me, takes this input and gives me that output, you're able to do it, right? You do know how to interpret the output of that neural network, right? Even though it's a super simple thing for many people, it's important to know it before you start doing the training. Okay, great. So if everybody's clear, then let's go for the training. And for training, we are going to use the classical learning algorithm that we had. What was this? It was empirical risk minimization. So we basically just go for loss function. So we send every single data sample that we have inside our neural network. We send every single of them through the network. We get the output. That output, right now, you do know how you can interpret that. So based on that interpretation, you are supposed to design one loss function. And you get that loss function. You just compare your output to the true label, right? If, for instance, your output is a probability, you're going to look at that probability and you try to find out one sort of loss function between that probability and the true label, which is dog, right? So you are going to do that. We do define the loss function next. And once you just send every single point through your neural network, you're going to get the output for every single point. They are the y values. And then you compute the loss between your y values and your true label b, right? And once you average them out, you're going to have one function which is going to only depend on your weights, right? So inside that expression that you see here, the only thing that can change this average is the choice of vector w, right? If I change the choice of vector w, then this value is going to change. And what I hope for is that I just find the right choice of w, which is going to minimize it. So the training or learning algorithm is going to be this guy, right? The whole training process is that I find a solution to this optimization problem. I just start with some weight and try to do one algorithm which ends up with one choice w, say w star, which is minimizing that loss function. That empirical risk function, sorry. Everybody's clear? Everybody remembers? Right? Okay, great. So one thing here, this function R hat W, the empirical risk function, is it going to be now anymore a convex function? So you remember when we did linear regression, it was convex, right? It was the norm of x W minus V, right? And that one was, we say, is a quadratic function. It's always convex, right? But is it going to be convex anymore if I have a super deep neural network? No, it's going to be super weird, right? You probably are not able to even write it down analytically. So you don't need to just get confused to think like there is a function, simple function here. No, I mean, we do know that it depends on W, but it's not a very easy kind of dependence that we can represent it analytically. So now, let's get into how we can define the loss functions. And basically, we have two different problems here, classification and regression. I guess for regression, many of you could guess, what about the classification, right? So what do we usually use in classification as the loss function? Cross entropy, you remember that? Cross entropy, we talked? Yeah? So now we can just see why this reflects a kind of loss function. And maybe it also gives you an idea how you can design your loss function in future for any new task. So say I have first binary classification problem, okay? If I have a binary classification problem, I am going to compute some probability y, right? And once I get to y, oh, I shouldn't have written here 0, I should have written half. I'm sorry. So that y should be compared with half. This is not correct, right? This is a typo here. So at the end of the day, I am going to get my y at the output of the neural network. I'm going to interpret it as a probability, right? And then I'm going to check whether this y is more than more than half, or it is smaller than half. If it is more than half, then I'm going to say this, okay. So that should be half. So I am going to set my invariance, or my estimated label, to be 1 if y is more than or equal by half, and then it's going to be 0 if y is smaller than half, okay? So I am going to do this kind of invariance. One naive approach to define the loss function is to simply just check whether I'm wrong or right, right? So what I can say the loss between what I have concluded out of y and the true label v is when the label that I am concluding that v had is essentially different from v, okay? If I have that difference, so it means that my y is more than half, but my label is 0, then it means that I'm going to infer that the label is 1, even though the true label is 0, so I'm going to have an error, right? So I'm going to put error here. Otherwise, the other case as well. So if I just conclude that label is 0, but the true label is 1, again, I'm going to say I have a loss. And in any case else, I'm going to say I have no loss, so essentially 0, right? So you might remember from our linear classification problem that this is not a good choice, but I just wrote it here for you because later on when we do backpropagation, I want to get back to this one as well, okay? Now, it's not something easy that we can work with, so the better idea that we can work with is to just use some function which is of an analytic form, right? So which we can compute efficiently and which has gradient for future when we want to do gradient descent, okay? Now, this function is a valid loss function. Why is it is a valid loss function? Anyone can tell me? Just want to see whether you get the idea how I can check whether this is the right loss or not. Say v equals by 0. What's going to happen? Where is this loss minimized? If v is 0. When y is 0, right? If y is 0, what do I conclude? I conclude that the label is 0, right? So this is a good thing. If v is 1, then my loss is going to be minimized when y is essentially 1 or very close to 1. And this, again, is just the thing that I want, right? When y is close to 1, I'm going to conclude that my true label is 1. This is what I want, right? So this is a right loss function. This is doing the job that I want. So again, if I want to just put it on the form of a graph, so this function y minus v squared, I mean, when y is the output of a sigmoid function, is going to be essentially between 0 or 1. It cannot be 0 and 1 itself, actually, but it's somewhere in between them. So if I set my v equal by 1, then it's basically this function, right? So when the maximum value is happening when y is close to 0, minimum value is happening when y is close to 1. This is what I want. I want y to behave like that, right? Same thing again if I said v equal by 0, right? So when I said v equal by 0, again, y is somehow convinced to be close to 0, right? Because if it is not close to 0, then the loss is going to be large, right? Yes, I'm over the pattern. Okay. Okay, now we have. Sorry for that. Okay. Okay. So this loss is essentially doing what we want, right? So this is important that the loss that we are choosing is doing the thing that we want, right? Now, one other choice for loss is this guy. This is what we defined before as cross entropy, right? So how do we define it? Look at the expression first. When v equals to 1, then it's going to be minus log of y, or I can write it down log of 1 over y, right? Correct? Now, if v equals by 1, and I'm computing log of 1 over y, let's write this first down. So v equals by 1. So I'm going to compute the loss between y and v to be a log of 1 over y, right? Y is the output of sigmoid function, right? It's between 0 and 1. When is this expression minimized? What is the minimum value this expression could get? If y is smaller than 0, 1 over y is larger than 1, right? Sorry, it's smaller than 1, then 1 over y is larger than 1. Log of something more than 1, is it positive or negative? Log of something more than 1, is it positive or negative? Positive. Log of 2 is positive, right? Log of 1, what is it? It's 0, right? So when y is 1, right? When y is 1, this expression, this loss term is going to be 0. If y is more than 1, smaller than 1, then 1 over y is larger than 1, and this loss is going to be something positive, right? So where is the minimum happening then? At y equal by 1. So this guy is minimized, so minimum is going to happen when y equals by 1, right? Same thing happens for the other case. If you set v equal by 0, then it's going to be minus log of 1 minus y, right? Or essentially, I can write it down log of 1 over 1 minus y, right? If v equals to 0, then as I set y close to 0, this loss is getting very close to 0. This is good. But when I send y to be closer to 1, then this loss is going to increase, and this is something that I don't want. So again, this guy is doing what I want, but essentially it's doing it much better than the previous choice. Because if you look at it now, like I put v equals by 1 now, you see that it's again going to show the same behavior, but the difference is that when y gets very close to 0, then that loss value is hugely going up, right? So it's penalizing my deviation from y being closer to 1 heavier as compared to the other loss function, right? Same thing happens for the case of v equal by 0. So if I set v equal by 0, then I'm going to get loss value 0 at y equal by 0. But as I increase y, the loss value is going to increase, and this time is going to increase much faster, much harder. Okay? And because of that, this is a better loss as compared to the other one, if you just want to look at it from a computational point of view. But we do know that this guy is coming out of the maximum likelihood training, right? So if you look at the whole process to be a probability distribution, we want to just maximize the likelihood of the model, then we're essentially going to end up with the cross entropy, right? So it was the other interpretation we had before. That being said, now let's think of the case where we want to just extend it to the k-dimensional, k-class scenario. So I want to just go for a k-class classification. And if I want to do that, how can I define that loss function? So you see it here on the board, right? So on this slide. Here I would say if my label is V, meaning that now I assume that V is the class that I have. It could be V value is either 1, 2, and so on till K. Okay? It's either class 1, class 2 till class K. Okay? And if I want to do that, then essentially I'm going to get the logarithm of 1 over probability of that class, right? And that is going to be yk. Okay, sorry. I wrote it yk here. Okay? This is going to be your loss, the loss between, yv. Loss between your y output and v. So you are going to look at the class v. Your y vector looks like this. So your y vector is something y1, y2, and so on till yk. And then you look at the class v. So here in between is your true class, right? And then you see what is the probability of that class. This is yv. You get yv, you put it in this expression, and then you compute the log. Okay? And now this guy is going to be your loss. Again, this is doing the job that you want. Because when this probability gets very close to 1, this loss is going to be its minimum value, right? It's going to be very close to 0. And when this guy is close to 1, what is going to happen to the remaining guys? They're going to be close to 0 because they are making a probability. These guys are the output of softmax, right? So everybody else is going to get very close to 0, right? Everybody's clear? Questions? So this is how we can define the cross entropy in the more general case of k-dimensional k-class classification. So essentially, if we think that we have k different outputs, what we would like to have such an output at the output of our neural network. So we want, if really we are sending anything from class V into this network, we want the output of the neural network to be exactly 1 at that value, at that index V. Anywhere else, we want the probability to be 0. This means, in this case, the cross entropy is going to be 0. And if we have anything but this guy, if we have any other probability distribution, that cross entropy is going to be something more than 0, right? So essentially, again, when you try to minimize your loss, you're convincing your neural network to give you the kind of output, this kind of output. So the output, the probability for class V is going to be very close to 1. And this is exactly what you want, because out of that you can infer that the true class is V. Everybody's clear? Questions? Anybody has the course information theory or had it before? If you had the course information theory, do you remember what we call that, or this guy? Log of, I mean, no worries if you don't remember, because not everybody say this in the course. But log of 1 over the probability of one event. What do we call it? Anybody has any clue about that? Information content. Information content of that thing. Okay? So when something has very low probability, 1 over that thing is very large. And logarithm of that is the amount, the number of information bits being transferred when that event is happening. Okay? Just if you got at some point into information theory, there is a very one-to-one connection between the concepts here and there. Okay? Information content. Information content of event V. Like what is the amount of information when that event happens. Okay, so now we can show this expression in a more sophisticated form. I can write it down again in form of a summation. Here in this summation, I am putting one indicator function. So that 1 I equal by V is going to be 1 if I is exactly V. So if I am really having index V, if I have any other index, that guy is going to be 0. I mean, if you compute that summation, you get back to this expression, right? Because log of yi is going to show up only for I equal by V, right? For anything else, that indicator function is going to be 0, right? So now we can write it down in this form as well. So I can define one vector V. And this vector V is, again, k-dimensional, exactly as much as entries I have inside Y. And this vector is going to be 0 everywhere, but at the place of the true label V. Okay? This is what we call it one hot vector. So one hot vector here is 0 everywhere. It's only 1 at the place of V. Right? And then your cross entropy is essentially the entries of this one hot vector multiplied by log of yi. This is what you usually see when you search cross entropy, right? So the cross entropy between vector y and vector v is computed in this form, but in training process, you always use it in this one hot form. Everybody's clear? Questions? No question? Great. So if you got no question, cross entropy, you can compute it for like non-one hot vectors as well. Like this final expression that we have here, you can compute it for any two probabilities. Like if y and v, both of them are probability vectors, you're still fine. You can use that expression. But we always use it with one hot labels, right? Because we do know the class of that label, right? This is dog, this is told to us. So now what if we just go for regression? In regression problem, essentially we get our input, we do all the process, at the very output we are computing one value y, and we said that this y is now a real value. This means that the whole thing from x to y can be thought as a kind of real valued function, right? And that real valued function is trying to just fit those samples that you have in the best way possible. So in this case, if you want to define the loss, what is the good choice of loss? How I can find out whether the output of my neural network at one specific point is close enough to my sample. You just compute the difference, right? You just compute the difference. So if I am looking at one single point, say that black dot is V, the label of my sample, so it's a real valued number, and now I have the output of my neural network, y, at that particular point, right? So if I set x, then y is going to be calculated by the neural network. I do know what is the true label, and now I want to know what is the difference between these two guys. So you can guess that in this case, you can simply compute it by putting any distance measure, right? And the best one that we use usually is to just use the difference squared, right? This was exactly the thing we used in linear regression as well, right? So you're going to look at the output of your neural network. You have the true label. The true label is, again, I mean, if you have k-dimensional output, your true label is k-dimensional. And you can compare each pair against each other. You just find what is the difference between them, the squared value, because you don't want to have negative values here. And then when you minimize it, essentially, the best thing you can get out of your neural network is that your value y is exactly vector v, which is the true label. So this is, again, a right choice of loss. And when we do that, we usually call the empirical raised to b mean squared error, right? But this is not something new for you. It's essentially the same thing we did in linear regression. Questions? No question? Great. So if you got no question, then let's get into the training. So we could have break, but that break should be very fast. And then you should not complain when I just spend more time towards the end. Is it okay? Okay, so 5 minutes, and then we start with this part, okay? Just maybe I ask for.
Your call is being connected.
Thank you for calling Texas Group. How may I help you?
May I have some battery?
Is it a AA battery?
So this is demo. Yes, number one.
All right, and there might be some batteries in the teaching station. If not, I can send some.
No, there is no battery.
All right, so to do that, I'll send someone with the batteries.
Thanks a lot.
All right, thank you, Paul.
Exponential is because it keeps it non-negative. You can do it with absolute value as well, but then you have this trouble that if any of those, I mean, if like most of them are close to zero, then it's super unstable, right? Okay. So you want to have a very nice differentiable function, which also does not get unstable. But that definition doesn't immediately comes from that background. I mean, this has this kind of property, but this kind of expression, like e to the power something divided by summation, this is a kind of the most general form of probability distribution you have. They call it Boltzmann distribution. And then you can show pretty much any distribution with this formula. It only depends on if you write down e to the power f of the input divided by summation of e to the power f of input. Generations of k, if you have I different systems, I, this is the j, we call pj this, right? Then essentially whatever distribution you have, you can write it down in this way. For instance, in the case of Gaussian, f is simply the norm of z. Norm of z squared. So if I put here e to the power norm of z squared, then in denominator, I don't have discrete points, I have no continuous points, right? Z could be anything. So I'm going to compute the integral of z squared, okay? Sorry, minus. And if you do that, then this expression is going to be by something. And this is the Gaussian distribution. So this is the most general form of distribution.
This activation function this isn't the same activation function. It's like special.
Yes, it's special for the output to compute your distribution. This is what we call a vector activation. So it's a bit different from the normal activation, which takes one scalar and computes one scalar output. If you have multiple things, you just do it entry-wise. It's not anymore that. So you get mixed values together, and you just do it for all. Yeah, of course, you can do it, but this is not going to be very stable. Because if the value of x is very small, say one case, you are exactly at 0.0. Then you go 0 by 0, right? So if the value of x is very, I mean that exponential function has very nice properties. You can do it, actually. In the assignments, the learning course, we have the case where we put this one absolute value of x divided by this. But this guy is not stable, especially if you compute the gradient.
It should be just this one.
Yeah, this guy is the issue. No, I mean, this is absolute value because the sign is going to show. But then, I mean, you have the expression here. It's not only this one, because if you are taking the gradient with respect to x1, you have it in the denominator and denominator. Gradient of the output times, denominator times denominator minus denominator times denominator. So it's going to be a bit more complicated. Divided by denominator squared. Yeah. But this is not going to be very stable. You can try it.
I can show you for again.
Oh,
I think you mentioned in the previous lecture.
yeah. But it's okay. You want to ask me? Yeah. Sorry? Maybe we do it after the lecture. So shall we go on? Okay, so now let's start with the training of the neural network. Let's say that you set the network properly, so you do now understand how you can interpret the output of this neural network as the right thing that you want. So this is the first thing. The other thing is that you do have access to the right choice of loss function, so you have chosen your loss function in the way that it somehow imposes the kind of behavior you want to see at the output. And then after that, the only thing remains is that you want to somehow do the training, meaning that you want to minimize the empirical risk, right? So if you want to minimize the empirical risk, as we said before, the only choice we have is to go for gradient descent algorithm. And how does gradient descent work? It's going to start with some initial weight, W0, and then it's going to somehow converge till it converges. It's going to iterate till it converges. And in each iteration, what do? How do we update our weights? We're going to get the weight at that particular time or iteration. And we are going to move in one direction. What is that direction? Minus gradient of the objective function, the risk, exactly. So we talked about it, why this is a good choice, right? You remember that, correct? So the gradient is always going to show us on any surface where you should move to just maximally increase. So when you move in the opposite direction, you are just moving in the direction which is maximally decreasing, right? So this is the general case. So you always have the weight. You compute the gradient at that point. And then you just subtract minus some step size gradient vector. And then you get your new weight, okay? That step size is what we call it the learning rate, right? So that is the learning rate. If we choose it large, what's going to happen? We can skip the minimum, so we can have the issue with convergence. But if we choose it very small, what is the challenge then? It could get stuck in a local minimum, and it could take for a long time to converge, right? So it says, thanks. Because the other one, the other battery was off, and this was one. This. Oh no. No worries. Can you do it?
Mic looks a bit old, actually. I'll get it replaced. Perfect. Is it,
Yeah, perfect. Yeah,
you looking?
yeah perfect. Thanks a lot. Okay, so yeah, that was the gradient descent algorithm, and everything here is possible for you. The only thing that you need to compute now is the gradient of your empirical risk with respect to the all weights you have inside your neural network, which you can think is a very exhaustive task, right? Okay. Now, if you want to do that, the first thing that we can do is to just look at the empirical risk that we have. Let's try to break it down a bit. So let me define the risk between the output of the neural network, the loss between the output of the neural network, and the true label, the loss between these two, for one particular sample. Let me show it by this R hat n. And what is R hat n? This is what I call it sample loss. Okay? By sample loss, it means that I got one single input. I passed it through the network. I got the output. I look at that output. I compare it with the true label. Now I compute one loss. This loss is not the final empirical risk that I want. I mean, I compute lots of them, and then I average them, right? Correct? So that is the sample loss, and essentially the empirical risk that I want to compute is the average of those sample losses. Correct? So at the end of the day, why do we have so much trouble today? So at the end of the day, we are going to get this average, right? So empirical risk is essentially the average of those sample losses, right? Now, if I am able to compute one gradient of one sample loss, then I am okay, right? Because I can compute the gradient of that sample loss, and then I can just try to compute it for all samples I have inside my data set, and then I average them, right? Then it's going to be the gradient of the empirical risk. So, moral of the story, I do not need to attack the whole empirical risk at once. I simply need to find out a way to compute the gradient of the sample losses, right? Or a single sample loss for one single point. If I can do that, then I can compute the gradient of the empirical risk. Everybody's cool? Okay. So now let's just take a look once again. The sample loss, it's simply I put one input at this neural network. This is going to pass. It's going to give me one output. I do know what is the loss function, so I am able to compare yn with the true label vn for that sample n, and I can compute the sample loss. Now, if I want to know what is the empirical risk, I need to do it as much as samples I have inside my data set, and then I average everything out. This is going to be the empirical risk. Everybody's cool? Okay, so now, I want to do this, so I want to compute the gradient of that sample loss with respect to the weight. And now let's go and write that down. This means that I want to know what is the gradient of that guy, that last term, with respect to the weights, right? So where are the weights showing up in that term? It's inside the first argument, right? This is what we call it nested function, right? Everybody knows what is nested function? Yeah? What is a nested function? So this is a nested function. If y is a function of z and z is a function of x, then y is still depending on x, because if I change x, y is going to change, so it's a function of x, but that is a nested function. So it's not directly connected to x, but it's just connected through another function, right? So for instance, say my y is z squared, and z itself is 3 times x. Then if I take that 3 times x, I put it in place of z, then I'm going to end up with y being 9x squared. This is a function of x, but it's not a direct function of x. It's a nested function of x. Everybody's clear what I mean by nested function? So if that is clear, then essentially what you see on top, you see that my sample risk, sample loss, is a function of the weight, but this is a super nested function, right? Because that weight is showing up in the first term of the loss function, and when I go inside my neural network, I do have lots of computations happen next to each other, right? So the output of the neural network depends on its own weights and the previous hidden layer, right? And those hidden layers, hidden neurons, depend on their own weights and previous hidden layers, and so on, right? So it's a very, very deep nested function, but at the end of the day, it's a nested function. Now that I have this, let me just break it down to a very simple problem. And that simple problem is that I do know that I have a nested function. So y is a function of x through z. And what I want to do, I want to compute the derivative of y with respect to x. But I don't want to do it analytically. So it means that I'm not going to put x inside z, and then I do the whole calculation, and finally I find out the expression and take the derivative. This is, of course, something not feasible on computers. So what I want to do, I want to do it with some other tool, some other approach. So any idea how we can do it? Anyone knows about any trick that we can do with? Chain rule. Have you heard of it? Yes? Okay. How does it look like? Let's do it together to just recap. I do know some of you had already chain rule before, but even if you had it, just let's try to do it once again together. So let's say that, this x, if we want to find out what is the derivative, what we can say z is a function of x, right? So z here is a function of x. And we talked about this. When we are talking about derivative, what do we mean? We mean that if we have one derivative, so the derivative d of z with respect to x, it means that this guy, which we sometimes show it by g prime of x, so this guy, when we multiply it to any tiny bit of change inside x, is going to specify what is the change inside z, right? Correct? So if I change x a tiny bit dx, then the output z is going to change by dz. And that dz is the derivative of z with respect to x times the dx, right? So now, say I change x tiny bit by dx, then I'm going to get the change inside z to be dz equals by the derivative of my function g times dx, right? Now, if I change now dz now if I go for the second function, I would say z has been changed a tiny bit, so this change dz is happened on the value of z. And how does it reflect on the value of y? Well, it's going to be dy, which is the derivative of y with respect to z, times that change dz, right? So it's going to be f prime at point z times dz. And if I replace dz from the first line into that expression, it's going to be the derivative of f with respect to z times the derivative of g with respect to x times dx, right? Now, what is the derivative of y with respect to x if you look at this expression? What is dy to dx? Can you tell me? I write it here. What is dy to dx? Just divide both sides by dx. What is it? Please? Look at that. Was it so unclear that nobody's responding? What is the derivative? Can you tell me? Like, either I am doing a very bad job, or it's very late, or I don't know. But I mean, even if I'm doing a very bad job, you can tell me, right? I can repeat. So once again, here, everybody's following? So I have changed x a tiny bit, right? And then I wanted to know how much z is changing. I multiply that change in x with the derivative of my function g, right? And then I know that my z has changed. Now I want to know how much y is changing. Again, I would say if I multiply that change with the derivative of my function f, I am going to get the change in y, right? So if you just replace everything into that last equation, you're going to end up with that term on the right-hand side, right? Now, if I want to know what is dy, the difference in y divided by difference in x, what it would be based on this slide? F prime at point z times g prime at point x, right? So this is what you call the chain rule, right? So you can write down dy to dx to be dy to dz times dz to dx, right? Everybody's clear? So now if I have more functions nested to each other, so say I have this kind of function, so I have x, this x is giving me the value z1, this z1 is giving me the value z2, and I keep on going till I get into zl. And then out of zl, I'm computing the value y. Okay? So I had x, I put it in the first function, I got z1, I put it in the second function, z2, and so on till I ended up with y. Now if I want to compute dy to dx, so this very output with respect to this very input, can you tell me how I can write it down? It's going to be dy to, y is coming immediately from zl, right? So it's going to be dy to dzl, exactly. So it's going to be dy to dzl. What should I write next? dzl to the, with respect to the previous one, right? dzl by dzl minus 1. And I keep on going till I get, for instance, here, right? Say here, dz2 divided by dz1. And what is the last expression? dz1 with respect to dx. So I'm going to keep going backward from the output till I get to the input that I look for, right? So this is what we call a chain rule. Yeah? Everybody's clear? Now, what if, so this is the expression that I showed on the board for you. So chain rule, if you have a very deep computation, you still can use it. And we usually show it on a computation graph, right? So this is the graph that I showed here. So here, as you can see, I start with one variable, x. And then from x, I compute z1. Then from that variable, I use that variable to compute the next one till I get to the output variable. And if I want to compute the gradient, or derivative of the output gradient with respect to the very input, I can simply use chain rule, right? Questions? No question? So now what's going to happen if I go for a multi-dimensional function? How does it look like then? Say I have this function f, and then this function now is a function of z1, z2 till zl. Okay? So I have L different values, and all of them are showing up at the same time in my function. So I have Z1, Z2, till ZL. And all of them are computing y. All of them together. Okay? Now, say that all guys here are a function of x as well. Right? So this is G1, this is G2, this is GL. So I have one function computing Z1, I have one function computing Z2 till the last one. Now if I want to compute dy with respect to dx, how can I write it down? dy with respect to dx. Any idea? No. Yes? Yeah, that's right. But anyone from the behind of the lecture hall? Because people there, it seems to be like less clear about what I'm doing today. So anyone has idea how I can write down the chain rule? I mean, if this is like very clear for you, please tell me. I would be happy. I'm going to skip it. But if it's not clear, it's clear, right? Everybody's cool with that, right? So great. So you could have told me from beginning. Okay. So now that this is super clear for you, let me test you. Can you tell me how I can write it down? Can you tell me, please? dz1, exactly, times dz1 with respect to dx. And I keep on going, right? So it's going to be dy with respect to dz2 times dz2 with respect to dx. And you keep on going like this, exactly. So this is again the same thing as before. So you can again say that every single z is going to change with respect to x in this form. And then you again replace it into the expression for the change inside y, which is going to end up with this particular chain rule in the multidimensional case. Right? Everybody's clear? Great. So now that you have this, again, we could show it on a computation graph. This is the most important thing because this is going to help us a lot in backpropagation. We start from the x value, we compute a bunch of variables, and then we compute the output y, right? And if you want to just do chain rule, we basically just compute those partial derivatives, and we keep on going back to the input, okay? Now, why do we discuss this chain rule? Why this is important? This is because the computer that you have is essentially doing or computing all of those gradients based on this computation graph and the chain rule. So I just give you this simple example that we want to do it in both analytic way and also the way that the computer works. And once that is clear, then probably most of backpropagation is clear for you. So say I have three different variables, z1, z2, two different variables, z1, z2. So one of them is x squared, the other one is x cubic. And then your y value is this expression, okay? It's given in terms of z1 and z2. Now, if I ask you what is the derivative of y with respect to x, probably you don't do any chain rule, right? You're going to put z1 to be x squared. You're going to put z2 to be x cubic. You do a bit of calculation. You end up with 3x to power 6, right? And then you want to take the derivative that is obvious, right? You're going to say, so this is 3 times 6, x5. So it's going to be 18x5. This is the derivative, and if I want you to compute it at the particular point x equal by 1, this is going to be 18, right? But your computer cannot do it, right? Your computer cannot take x as a symbolic argument and put it back inside z, right? So how does your computer work? How does it compute the gradient? So the way that it does it is this way. So you're probably going to define z1, z2, and y in form of some expression, right? So you have z1, this is one variable, z2 is another variable, x is another variable. You set x equal by 1, then those variables are going to be specified, right? Out of those variables, y is going to be specified, that's it, right? So now you have y. Now if you want to compute the derivative of y with respect to x, and you want to be able to do it with respect to, any x that I give you, you can do it. The way that you would do it is that, or the computer would do it, is that it's going to look at one dy to dz1. So this is the first partial derivative. The other partial derivative, so it's going to be dy to dz2. So basically, you're going to look at the last expression, and you compute the partial derivatives. And then you put them here. This is the partial derivative. And then you would define the derivatives of z1 and z2 also with respect to x. And then you write down that chain rule. Okay? You write down back that chain rule. And then this chain rule is going to give you dy to dx. Meaning that on your computer you have variable x, z1, z2, and then y. Every single of them has also a gradient, right? So you have a gradient from y to z1, you have a gradient from y to z2, and then again gradient from z1 to x, gradient from z2 to x, and then you do all the whole computation, then it's going to be the gradient of y with respect to x. Right? So this is the way that your computer is going to work. And now we want to do the same thing when we have a neural network. Because again, at the neural network, what is happening is that we have a bunch of input, and then we are going to do some computation. So you can think of every single neuron as a kind of variable on your computer, right? And then you do those computations, you go for the next layer, right? Again, you do a bunch of computations. So every single of those neurons is one of the variables, right? And then you want to be able to compute the gradient with respect to the weights and also those variables inside the neural network themselves. So let's start with one single neuron. So one simple neuron that we have. And we want to just find out what is the derivative with respect to the weights that I have, right? So I can write down this computation graph. I would say, okay, the weights that I have are W1 till WD. I have D different weights. I have one bias. And every single one is going to get multiplied with the entries on the edge and added up to compute Z for me. And from Z, I'm going to compute Y. And from Y, I can compute R hat, right? So I can look at every single node in this computation graph exactly as the same variable that we have on the computer, right? And now if I want to compute the gradient, or the derivative with respect to every single of them, how can I do it? Let's say that I want to just compute the gradient with respect to one arbitrary weight. So I am going to compute the derivative of R hat first with respect to Y, because R hat is an immediate function of Y, right? I can compute that derivative. That is simple. Loss function is given to me, for instance, that is cross entropy. I can compute the derivative, right? So from that one, I have Y, and now I know that Y is the activated version of Z. It's again a direct function of Z, right? So I can again compute the derivative of Y with respect to Z, correct? And now if I want to get from Z back to any weight, I can simply just compute the partial derivative of Z with respect to that particular weight. Say, for instance, I want to compute the partial derivative of Z with respect to weight W1. What is that? What is the partial derivative of Z with respect to W1? Z is W1 x1 plus W2 x2 plus so on plus b, right? What is the partial derivative with respect to W1? X1, right? So it's essentially the variable you see on the edges, right? So the partial derivative, again, that you compute here are going to be exactly those numbers. And then that's it. If you want to compute the derivative, the partial derivative of R hat with respect to any weight of this neuron, you essentially need to get the first derivative that you computed in the backward pass, the second one, the third one, and then you multiply next to each other. It is going to be the derivative with respect to that particular weight. Clear? Questions? No question? Great. So if you got no question, then let's go for one simple neural network. Say, for instance, I have this neural network. So those expressions you see on the edges, they are all weights. Okay? A0 is one neuron. So A0 is the activated value. It has only one weight, Z. And I have A1, which has weights beta 1, beta 2 with bias beta 0. And everything else you can read on the graph. Okay? Now what I want to do, I want to compute the derivative with respect to, for instance, let me see which one I want to do. I guess beta 1, for instance. Yeah. So, I mean, first of all, I can write down the whole operation, right? So at first node A0, that neuron, I am going to compute one linear transform that is going to be Z times its input X, right? And then I activate it, correct? So this is the first thing. Or at A1 and A2, those hidden neurons, I am going to compute H1 and H2, which are a linear combination of their inputs. And then out of that, I am going to activate them, which is going to give me A1 and A2. Again, at the output, I am going to do the same thing. So I get A1 and A2 out of those neurons. And I'm going to do first linear combination, and then I do the activation. Everybody's clear, right? So now, if I want to just compute one particular derivative, for instance, I want to compute the derivative with respect to beta 1. How can I do it using chain rule? Can you tell me? If I want to write down the derivative of my r hat with respect to beta 1, how can I do it? Where is beta 1 showing? Where is beta 1 being involved? At the output of which neuron? A1, right? So can I write it down in this form? So I'm going to compute it as derivative of r hat with respect to that A1 times derivative of A1 with respect to beta 1. Is it okay? It's chain rule, right? Correct? So I can write it down in this form. Derivative of r hat with respect to beta 1. Beta 1 is connected directly to A1. This means that A1 is the first guy getting impacted by beta 1. So I can just compute the derivative of A1 with respect to beta 1 and then multiply it with the derivative of the sample loss with respect to that A1, right? That is chain rule, correct? Now, how can I compute, those two terms? The derivative of A1 with respect to beta 1. Is it clear for you or not? Can you compute it? Look at this here. A1 is a function of H1. H1 is immediately computed from beta 1. Can you compute that derivative? It's again one chain rule, and you can do it, right? Derivative with respect to H1 times derivative of H1 with respect to beta 1, right? That is simple. So that first expression is simple. What about the second expression, derivative of r hat with respect to A1? And r hat is computed somewhere at the out of the neural network. How can I do it? Any idea? I'm going to again use chain rule. How do I do it? If I want to end up with the risk, where should I go from A1? What is the next node? Y. Y. I'm going to end up with a loss, right? Loss is computed at the output, correct? Right? So now if I want to do that, I would say that the derivative of A1, r hat with respect to A1, is essentially derivative of r hat, the loss with respect to y, the output, times derivative of output with respect to A1. Can you compute the derivative of y with respect to A1? Can you do that? You can do it again. Look at this expression here. Y is a function of z, right? And z is a linear function of A1, right? So you can again use a chain rule to compute that gradient, correct? Right? So that expression, that first derivative of y with respect to A1, you can do it. The derivative of r hat with respect to y, can you do that? What is r hat? R hat is defined to be the loss between y and the true label v. V is fixed. Can you compute the derivative of r hat with respect to y? Yes. If you know the loss function, you can now compute it, right? So now you can compute that derivative with respect to beta 1 using those sequences of chain rules, right? Now, what if I want to compute the derivative with respect to z? And I know that I say z, z, and z, the Greek z as z as well. So now I'm talking about that z, that guy, the first guy. I mean, let me show it here. By z, I mean this, the green guy, this one, okay? If I want to compute the derivative with respect to this one, how can I do it? So that weight z, is connected to a0 immediately, right? So I can write it down as the derivative of r hat with respect to a0. So r hat is the loss, which is very, very out. R hat with respect to a0, the immediate node, immediate neuron that I'm connected to, and then derivative of a0 with respect to that weight, right? And that derivative of a0 with respect to the weight, can you compute it or not? Yes? Yes, because a0 is computed directly from that weight, right? So again, remember, look at here. a0 is the activated of h0. h0 is that weight multiplied with your input, right? So you can compute the derivative with respect to that weight, right? So if you can do this, then you're fine here. So you can compute the first term. What about the second term? I want to compute the derivative of r hat with respect to a0. How can I do it? Based on that graph, anything you can suggest. Of course, I am going to use chain rule again, right? Can you tell me something? Any suggestion? From a0, where I am going, if I want to end up at loss, I can go to a1, and then from a1 I get to y, and then I get to loss. From a0 I can go to a2, and then go to y, then go to loss. So both of them are involved, right? Both of them are function of a0. Now, if I want to write down the partial derivative of r hat, the derivative of my loss with respect to a0, how can I write it down? Which guys are next connected to a0? a1 and a2, right? So if I know the derivative of r hat with respect to a1, then I'm going to multiply with derivative of a1 with respect to a0. Should I stop? No, because I have also a2, which is a function of a0. And that one is going to end up with loss as well, right? So I'm going to write it down as the partial derivative of r hat with respect to a2 times partial derivative of a2 with respect to a0, right? Correct? Everybody's clear? So I can again write down here the partial derivative of my loss with respect to a0 in terms of the partial derivatives of the next neurons being connected to this neuron, right? If I use chain rule, correct? Now, if you just compare this node, the neuron A0 with the neuron A1, you can conclude a sort of general form of the computation of partial derivatives. So if you are in a general network and you have one particular node A0 being connected in the forward pass, is going to be connected to a bunch of nodes here. So A0 here is going to be connected to neuron A1, A2 till AJ. So it has J different neurons. We usually call them children, okay? They are the children which are getting information from A0, right? So if A0 is connected to J different children, now if I want to compute the gradient with respect to any weight of that particular A0, then I can write it down as the derivative of the loss the derivative of loss with respect to that weight. Okay, again, another typo here, so it should be A0, I'm sorry. So this H here should be A0, this guy. So it's not H, it's A0, okay? So I can write it down as the derivative of the loss with respect to the weight that I am looking for. So it's going to be the derivative of loss with respect to weight Z is going to be the derivative of loss with respect to A0 times derivative of A0 with respect to that weight Z, right? And then, of course, this guy is something that you can always compute directly from your forward expression, right? And the other thing, the derivative of R hat with respect to A0, is something that you can write it down in terms of the children. How you can write it down in terms of the children? If I want to compute now the derivative of R hat with respect to A0. Sorry, if I want to do that. How can I do it on this network? What is the first guy function of A0? A1, right? So I'm going to write it down as the derivative of R hat with respect to A1, right? Times, what should be the next? Derivative of A1 with respect to A0. Should I stop? No? I should keep on going. Till when? Till all the neighbors are included, right? So it's going to be the derivative of R hat with respect to AJ times derivative of AJ with respect to derivative of A0, right? So you are going to look at every single neighbor that you have. You compute the derivative of that guy on, and then you just get the derivative of that guy with respect to that, your own place, and this is going to give you the gradient of the R hat with respect to your own value, right? Everybody's clear? Questions? So I know this was a super fast introduction to backpropagation, but is it, I mean, it's basically chain rule, right? Okay, so if there is no question, then we can essentially write down the whole backpropagation algorithm in this form, right? So you can start in your network by setting your input x1 and x2, and you keep on going forward. In every node, in every neuron, you're going to compute the linear value and the activated value, and then you keep on going till you get to the very, very end of your network. Once you're at the very out of your network, you have your output y, and you have all the values inside, right? Every single neuron, the linear transform, and the activated version, right? So you're going to compute all of them. This is what we call it forward pass. You do need the forward pass. Just remember the example I showed you for computing the gradient on a computer, right? So you needed to know what is the value of x to compute z1 and z2 and z to compute y. And then when you are computing the gradient, again, you need to know what is x and z1, z2, right? So you need to have all of those variables computed, right? So once you have all of them computed, then you're over with your forward pass. And then in the backward pass, what you're going to do, you're going to compute first the gradient with respect to the very output. Now that you have this one, every guy for which you have the output a child, you can compute the gradient of all of them, right? Essentially anyone in the previous hidden layer, right? Now that you have all the last hidden layer neurons known to you, the gradient with respect to all of them is known, then you can go for the previous one, right? And you keep on going till you get to your very input, right? So in every single neuron, when you're moving backward from the output, you're going to just compute the partial derivative of your sample loss with respect to every single neuron that you have in that layer. Once you have all of them, essentially computing the derivative of your loss with respect to any weight, is quite simple. Once you know the derivative with respect to that node, you essentially need to multiply it with another derivative, which is again known to you. Okay? Everybody's clear? How we do backpropagation? Questions? No question? Great. So if you got no question, just a few points when we started with the whole neural network. So when we started, I told you that we always consider smooth activation functions, right? Do you see why we need a smooth activation function? What's going to happen if I don't have a smooth activation function? I'm not going to have those partial derivatives, right? For instance, say I am looking at one particular node, AJ. So AJ is the activated value. This is passed through one activation function, F, right? So I had one linear value, HJ, initially computed, and out of that, I activated that when I got AJ, right? So once I do that, if I want to compute the partial derivative of AJ with respect to A0, for instance, I need to first compute the partial derivative of AJ with respect to its own linear value, and then from its own linear value, I get back to A0, right? So when I want to do that, that partial derivative of AJ with respect to HJ is going to simply be the derivative of the activation function, right? So this is the derivative of the activation function, which is essentially important. If it is always 0, then you're going to have this value 0. This is going to 0 everything after that, right? You need to have a gradient. This is why we have a smooth function, right? We don't use a step function simply. We use, for instance, a sigmoid function, right? Because if you have a simple smooth step function, first of all, at the center, you cannot define gradient derivative, but also anywhere else, the derivative is 0, right? Even if you define any derivative at that particular point 0, anywhere else, the value of derivative is 0, meaning that that first f prime term is going to show up as 0 almost all the time, right? You have no gradient. You cannot do any updates, right? So this is the key reason that we need always to have a smooth activation function having some gradient, right? So same thing you can argue for the loss function, because once you want to compute, you're moving backward from very end to the input, right? And you essentially start with the gradient with respect to the output, gradient of the loss with respect to the output, and then you are going to compute the other partial derivatives all in between by backpropagation, right? Now, if you don't have that final gradient, if that last guy is 0, essentially everything else is 0. All of your gradient is 0. If you take that gradient and update your weight, you are going to do nothing, right? So at the end of the day, you really need your loss function to have gradient. This is why we don't like that indicator error as the loss function, but we like something like cross entropy or MSE. Yes? Smooth means essentially, I mean, practically, yes, continuous, but it could be non-continuous as well. But at that point, maybe you can deal with that. Yeah? If the function has gradient everywhere else, at that particular point, maybe you can. Yes. But you usually want to have a very smooth function, like no edge, no discontinuity. Edge is okay, but discontinuity is more problematic. So we do not usually want that, right? So yeah, no, as least as possible edges and discontinuities, of course.
What happens if you have edges? What will that?
Yeah, I mean, you can define the subgradient, right? So you would say like gradient from somewhere is something. Like if you have a function like this, so gradient from right side is one thing. Yes, that edge is, you can define something in between. So that you can define it, but more important than that in terms of computation is that you have gradient, right? Your gradient is not always close to 0, because then it means that whatever computation you do, you're ending up with some 0 value, which is useless, right? Yeah. So, questions? No question? Everybody's clear about backpropagation? I don't expect you to just write it down for any neural network right now, but I hope that you got the idea how we compute it, right? And then, if you got the idea, you usually use some package, right? Like PyTorch. And PyTorch does it for you. And how does PyTorch do? It basically does what we did on the board. Yeah? So it has been implemented very efficiently that it does the backpropagation. And typically, for instance, you just get one variable. So prediction is a variable of your, is a function of your variable data. So data is one variable. Then model is a function which you have defined inside your PyTorch code. And then you compute the prediction at the output. If you enable the gradient for data, then prediction is going to have also its gradient enabled. So I guess Mohammed has already done this for you in the other tutorial, where he just tried to give an introduction to PyTorch. And there you have probably tried this as well, right? So you are going to compute your output of the model, as a function of the input. And then if you want to just do backpropagation, you essentially get the loss. So loss is going to be the, for instance, difference between your prediction and your label. Or maybe you compute it in another way, so depending on the loss function that you have. Once you have this loss, then you just write loss dot backward. And basically all of this backpropagation is going to happen over your whole model. Okay? So essentially, PyTorch goes after every single node inside your model. You're going to compute the partial derivatives with respect to activated and non-activated values. And then it's going to just do all of those multiplications and summations to end up with the gradient that you want. Questions? OK, clear. So if you got no questions, so that's essentially the backpropagation. Once you have the backpropagation, then you are able to compute the gradient of one sample loss with respect to all weights that you have inside your neural network, right? Now, let's now think of backpropagation as a kind of thing, as a kind of algorithm, which we already have it. And now let's see how we can use this backpropagation to train our model. Okay? So the next thing that we want to do, we want to just do gradient descent, but when we are doing gradient descent, we want to use backpropagation, right? So what does that mean? Backpropagation, remember, backpropagation is computing the gradient of with respect to the weights. What is that blank? Gradient of empirical risk? Yes or no? No. What is that thing? We're computing the gradient of sample loss, right? The loss for one single point, right? So when we do forward, backward pass, we are finished with the gradient with respect to the gradient of one single sample loss, right? If you want to have the gradient of your whole empirical risk, how you can compute that? You can simply just use this expression, right? So sample loss means the one under summation, right? So your backpropagation algorithm is able to just compute that gradient for you. So if you give one sample point with the label to your backpropagation algorithm, it's going to compute the gradient of sample loss with respect to the weights, right? For that particular point. But now if you want to have the gradient of the empirical risk, you simply need to do the averaging. So how we can do it? Any idea? We can just go over our whole data set, right? So we're going to go inside the loop, while loop, line number 3. If you look at line number 3, this is where the gradient descent is going to start. So we start the gradient descent in line 3, so we want to compute the gradient at point WT. So how we can do it we should go inside our data set. For every single point inside the data set, we go forward, backward on the neural network, right? So we do the backpropagation, we compute the gradient of the sample loss, right? Once I did it for every single point inside my data set, then I'm going to come out of that for loop, and now I have all of those sample gradients. So R gradient of R hat 1 till gradient of R hat n, if I have n different points. I average them out. This is now the gradient of your empirical risk. Now you can update one iteration of the gradient descent. Everybody's clear what we're doing? Now, if your data set has 1,000 points, how many times you do forward, backward pass to finish one iteration? 1,000 times, right? So for the first point, you go forward, backward. For the second point, you go forward, backward. So on, till you finish with all the points inside your data set. Right? Okay. So this is what we call it full batch training. So we basically just, we do as many as samples we have inside our data set for computing one gradient. And then we can just do one gradient descent. This is what we call it full batch training. And in practice, we really need so many gradient descent iterations, right? So it means that maybe you need, I don't know, 10,000 iterations. And this means that you need to do 10,000 times the number of samples you have inside your data set, that much of forward, backward propagation over your network. That's going to be crazy, right? So just to give you one particular example is the example of ImageNet. So in ImageNet, you have 1.2 million images inside your data set. This means that if you want to do what we had in the previous slide, for every single iteration of your gradient descent, you need to go 1.2 million times forward, backward over your neural network to be able to compute one single gradient. Now you have that gradient, you update, you again get a new bunch of weights. You need to repeat this. Doesn't sound feasible, right? So this is not really practical in practice. So the idea of full batch training is not a very good idea. A better idea is that we just go for sample gradient descent. So what is the idea of sample gradient descent? That is simple. Just get rid of that for loop. Okay? Every time, look at it here, you get into your gradient descent. So you get into line 3 where you start while when you get into your gradient descent. Now you want to compute the gradient, but you don't compute the whole gradient of the empirical risk. You just compute the gradient of one sample loss, and once you have that guy, you just forget. Oops, you just update, right? You update, you go for the next point, right? You have the new point, you have a new sample gradient, you get that sample gradient, again you update. Now, if I have 1,000 points inside my data set, how many updates do I do when I'm finished with my data set? 1,000, right? Because when I just computed the empirical, the gradient of the sample loss of the first point, I did one update. After the second point, I did another update. After the third point, I did another update. So when I am finished with whole my data set, I have already done 1,000 updates, right? Now, this is going to be faster, right? I don't need to wait 1.2 million samples to just do one update. I already have done 1.2 million updates by then, right? Correct? So this is the idea of sample level gradient descent, but there is one issue here when you use this approach, and that is the repetitive behavior that your algorithm could show. So we could have a bit of discussion on that, but this is not that crucial. So one just intuitive explanation of that is that, say you start with one weight W0, one initial weight, and you keep updating after every single sample you have inside your data set till you end with your last point inside your data set. okay? When you are there, at the point of the last point, say that it happens that you end up somewhere close, very close to your initial weight. What's going to happen if you keep on updating? Say I have 10 points inside my data set, 10 different points. Now, I start with W0, okay? And then I get my first point. I do backpropagation. I compute the sample gradient, right? I do one update, correct? Now, when I update, my weight is going to change. It's going to be W1, right? Now I go after the second point. By the second point, I again compute a gradient, sample gradient. And then that sample gradient, let me just update this one, right? So I'm going to get to W2. I'm going to do it till I get to W10, for instance, right? And then I'm over with whole of my data set. Now, say this W10 is exactly W0, for instance, okay? Happened that I ended up exactly at the same point. Then, this means that I am going back here, right? Again at W0. Now, if I again start with my data set, what is going to happen? The first gradient that I compute is going to come after from the first data point, right? And I'm again using the same data point, right? So again, I'm getting from W0 to W1, W1 to W2, so on till the last one. Again, I end up at the same point. I get it started over, right? So it doesn't matter how many times you go over that data set. You always are in one infinite loop, right? Did you get the idea of what's happening? The gradient that you compute here is the gradient of your sample loss r hat 1, right? Gradient here, sample loss r hat 2. If you don't change your samples, they are going to remain the same, right? If the initial weight is the same, right? So initial weight is the same. This guy is the same. I'm going to end up at the same point, right? I go on till I end up at W10, but W10 is exactly W0 again. So I'm going after the first data point. Again, I get the same gradient. I had the same initial point, so I'm going to end up at the same point again, and I keep on doing it over and over, right? So this is not a cool idea. So you don't want to have this repetitive behavior. So what can you do? Any idea? If I instead of using gradient of r hat 1, the first sample loss, if I use another sample gradient, would I end up again at the same point? No, right? So this is the whole idea. I just do shuffling. I just do random shuffling before I start over with my data set. So now look at this algorithm. This is what you call it a stochastic gradient descent, right? So it's essentially, again, a sample gradient descent, but you do add this random shuffling to it. So essentially, you start with, you get into the gradient descent loop, and look at line 5. So you're going to check if you are over with your samples inside your data set or not. If you are over with your samples inside the data set, you're going to shuffle the whole data set, meaning that instead of using with the starting with the same point, you're going to randomly choose another point, right? So you just permute everything randomly, and now that you have this permuted version, you start with the samples inside this shuffled data set, right? And you keep on going again towards very end. When you're finished, again you want to start over with your data set, you again shuffle everything. Okay? That thing going to help you to get out of this behavior, because maybe you got the first sample gradient in the first round, but then when you are doing the shuffling, then out of that randomness, this is something else, maybe 7. And this is not going to be W1 anymore, right? You're going to end up at another point. And hopefully you are getting to get out of this loop. Everybody's clear? Questions? So a stochastic gradient descent is basically gradient descent when you are not using the gradient of the empirical risk completely, but you're using sample gradients, and you're doing a random shuffling at the beginning of every time you get into your data set from start, right? Okay, so that is the stochastic gradient descent. Now, you might wonder, okay, on one side we can do full batch training, we can wait forever to complete the calculation of the gradient, then we get that gradient and we do gradient descent. We can do also stochastic gradient descent. That is a super fast one, because after every single backpropagation, we get one gradient and we update, right? Then is there any price that we pay? I mean, we're getting from a super slow algorithm into a super fast algorithm. Shouldn't there be anything that we pay? Any idea? What is the price that we are paying here? What is getting worse when we are increasing the speed? The quality of those gradients, right? Because in the first case, in the full batch, you're calculating the average of lots of gradients. You're going to get one very good, what we call it, estimator. But if you are just doing a stochastic gradient descent, in every iteration, you are just using a very noisy estimator, okay? And because of that, you're somehow increasing the noise inside your calculation. You get higher chances to just get out of the right place, right? So the whole idea here is that you are increasing the variance of the estimate with a stochastic gradient descent. And by the variance of the estimate, I simply mean that we'll look at what we compute in full batch training and the stochastic gradient descent, both of them to be estimator of a very, very true gradient, which is the gradient of the risk defined in terms of the data distribution. Both of them are estimating that one, but the one which you compute in the full batch training is doing a much better estimation. It has much less noise as compared to the one you are computing in the stochastic gradient descent. Okay? So, moral of the story, when you use the stochastic gradient descent, you have lower quality of the gradients, right? So, like the right direction to move was this one, but now it's very noisy. Maybe instead of this direction, this time it just tells you this, right? But hopefully if you do it for a lot of number of times, then it's going to just take a longer path towards the right point that you need to end up. Okay? Questions? Okay, so if you got no question, then the last thing that is left is the idea of mini-batch stochastic gradient descent. This is pretty much probably the thing that everybody nowadays uses when they want to do the training. What is the idea of mini-batch stochastic gradient descent? So we basically, instead of, we have the whole data set, right? Instead of just doing update after every single sample, we are going to break this guy down into some mini-batches, right? So we have smaller mini-batches. The mini-batch could be very small. It could be simply just 100 samples. So we compute the gradient by backpropagation for every single sample inside one mini-batch. Then we average over that mini-batch, and then we update. Okay? So we do not update immediately after every single backpropagation. We just compute the backpropagation, do the backpropagation for as much samples we have in one mini-batch, and then we average them out, then we do the update. Okay? This is the idea of mini-batch stochastic gradient descent. Now, this is obviously doing a sort of trade-off, right? The trade-off that it does is that by increasing the size of mini-batch, it's going to reduce the noise, right? It's reducing the variance, but at the same time, it's going to increase the time you need to wait for computation, right? So there is a kind of now trade-off between variance and speed. And that trade-off is somehow specified with your number of samples inside a mini-batch. One question from my side, if I made it clear for you, now you might be able to answer this question. If the size of my mini-batch is exactly the size of my data set, then what would be the mini-batch training? What would be this mini-batch SGD? Say? Same as full batch. And if I put the size of my mini-batch to be 1, then it is stochastic gradient descent. Okay, so that's clear now. So this is the idea of mini batch stochastic gradient descent. Then there are a bunch of definitions. I guess most of you have already heard them, but just to make it clear for everybody. So when we talk about iteration in training, we simply mean one iteration of gradient descent, which is going to happen after we are finished with data set or something else. Mini batch, great. So when we are finished with a mini batch. So when we are finished with one mini batch, then we do one update. This is one iteration, okay? Now, when you do iteration, you do your first iteration, second iteration. At some point, you are going to get finished with all of the mini batches you had, right? So everything you had inside your data set, you're going to finish, and you're going to start over, right? And when you want to start over, you do the random shuffling, of course, right? But once you're over with your whole data set, which you have potentially done multiple iterations already, then you are finished with one epoch. This is what we call it epoch. Epoch is when you are over with one complete round of trying your data set. Okay? It could include multiple mini batches. It depends on the batch size that you have. And the term batch size, it simply means the number of samples you have inside the mini batch. I mean, I personally would like to have it mini batch size, but why you just make it longer? So people call it batch size, okay? Batch size, simply the number of samples you have in one of those small mini batches that you take, right? Now, let's consider one example to make sure we understood everything. So I have 60K different samples, 60,000 samples inside MNest. And say I use my batch size to be 100, okay? If I do one epoch, how many iterations I have done? If I have 60,000 samples inside my data set, and I do split them, partition them in form of mini batches of size 100. How many mini batches do I have? 600. 60,000 divided by 100. This is the size of one mini batch. This is the total samples that I have. I'm going to have 600 mini batches, right? Right? 600 mini batches I'm going to have. If I want to finish with my data set, I need to just go over all of them, right? So it means that I already have done 600 iterations when I am finished with one epoch. Now, if you do two epochs, you essentially do 1,200 different iterations, right? If you do 10 epochs, then you have done already 6,000 iterations and so on, right? So you see like your model is trained after 40 epochs. Well, depending on your data set size and the size of your mini batch, that 40 epochs could be potentially some tens of thousands of iterations, right? Everybody's clear? Questions? Yeah?
So when we use SGD, because the algorithm creates a lot of noise, how can we prove this algorithm will not diverge?
I mean, you can use the mini batches. So as you increase the size of mini batch, then you are reducing the variance. And because of that, you are going to improve the convergence. Yeah, other approaches. I'm going to shortly mention them, but we don't have it in this course. But yeah, you can use other optimizers, for instance. You can use momentum, you can use RMS prop, or any of those stuff. Yeah? But essentially, they are just doing some process on your samples, too. Yeah. But the key point here is that this classic variance speed trade-off, so to just increase your batch size. So this is basically what I explained in the previous slide as well. So mini batch SGD going to help you to have a kind of fair trade-off between the speed and variance. So when you set your mini batch size, the batch size B, to be very large, then you're going to have a smaller variance. So your estimator in every iteration is going to be much accurate. But at the other side, you're going to have lower speed, right? But if you set your batch size to be very small, then you're going to have higher variance, but you can now do the process faster, right? You can do more updates within a given time, right? So this is a kind of trade-off, so between speed and variance, and the key factor that is just deciding this trade-off is the batch size, right? So if you see some algorithm is just diverging, your training is diverging because you have a very high variance in your gradients, maybe you can increase your batch size up to a point where you see an acceptable performance, right? But if you go beyond that, then you're going to just reduce the time, right? Reduce the speed. Yeah? Okay, so if that is clear for you now, when you are going to go out there and try different practical algorithms, you might hear that people do not simply talk about SGD or gradient descent. They say gradient-based optimizer. That is SGD. That is nothing but that. Okay? The only difference that they have is that in practice, after you compute those mini-batch gradients, maybe you don't use them themselves directly. Maybe you do some other process on them. For example, you compute the moving average. Huh? If you do the moving average, then essentially what you're doing momentum, the first approach. Maybe you do some learning rate scheduling, meaning that in every iteration, you're going to play with your learning rate. Okay? You find a right choice of this change of learning rate, right? This is learning rate scheduling. You're going to have lots of those optimized, but at the end of the day, all of them are doing what we do in SGD, right? They just add a bit of trick in between to just make the estimator a bit more accurate. So that's it regarding the other optimizers. So all of them are using mini-batch. Basically, they compute those batch gradients, and then they do some trick on top of that to just make it more robust. Some famous optimizer that you might have heard of are Atom, which is basically using momentum plus the variance normalization for scheduling. And you have RMS prop, you have R prop as well, so you can take a look if you are interested in those optimizers. But as I told you, at the very end of the day, they're going to all compute those batch gradients and do a bit of more calculation on that before they update. Okay? So that's it. So now I am pretty much over, just 5 extra minutes, and then it's over. So just want to wrap up everything that we did today so that next time when we start, we don't want to just recap everything. So say that I have one learning task and I want to use a neural network to do it. So what should I do? I am going to get my data set. I am going to set a model. How can I set the model? Okay, we discussed today. You are going to design one neural network. And then you mainly need to make the output of the neural network somehow fitting the task that you want. If it is a classification, it should be a softmax. If it's a regression, maybe it's a linear output, maybe it's a bounded output, whatever that is. At the end of the day, you just make this neural network to give you out as the output something that you really want to see, right? And the input should also match the data dimension that you have. Then you get your data set and you want to do training. Of course, you're going to collect those samples to do the training, but you are not going to collect all of those samples for training. Because once you have done the training, everything is over, you really want to test whether your training worked fine or not. And you cannot use it on the same data. You cannot do it on the same data that you trained with, because of course your model is going to work very well on those samples, right? You want new samples, right? So typically we are going to do a split into validation, test, and training sets. We are going to talk about validation next time when we start talking about generalization and overfitting. But here, essentially, like what we did in unsupervised learning, we usually just collect a bunch of data, a subset of data, around 70% of the data, for training. Now that we have the data for training, then we are going to get inside our training loop. What do? We define our model. For instance, in PyTorch, you set the model to be, maybe you put multiple layers, and then you wrap them up into form of a model. That is the model. It takes the input as the points inside your data set, it's going to give you the right output that you need. And you also do know what is the loss function. So you are going to get inside a loop, and for multiple epochs, you are going to repeat stochastic gradient descent. Potentially a mini batch version of it. So you get your model, and then you just pass a mini batch of data, you get the output, you compute the loss, you compute the gradient, you do one gradient descent, right? You keep on doing till you're over with the whole training set. Then again, you start over and keep doing it till the number of epochs that you have specified is over, right? Now that it is over, then you are going to return a bunch of things. One thing that you are going to return is the weights that you got out of this training, right? That final weights are going to specify the model. So you believe if you get that neural network and you put the weights to be the weights W star that you get out of training, then that guy is going to do the job for you, right? If it's a classification problem, any new image is going to get classified properly, right? So this is the one thing that you compute. The other things that you are going to compute are going to be the training risk or training loss and training accuracy. So you want to see that how does your training drop as you kept on training, right? Sorry, training loss drop as you kept on training, right? So when you were training, you were computing the loss of your on the data set that you had, right? And then that loss, I mean, if gradient descent was working, was going to get minimized. It means that that loss was going to drop, right? Now, you're going to save the last value of the loss that you got. This is going to be a reference for you. So if everything works fine, then on a new data, you should end up at that value, right? And same thing for accuracy. So you're going to see that when you train this model and you give all of those training samples into your model, how much accurate your model is going to fit your data. Okay? How much accurate it could classify those samples, right? Once you have done the training, then you're going to get into a validation loop. And the validation loop means that you're going to get those 15% of data which you did not use for training. Now you pass them through this model, and you're going to see what would be the performance. How % of time this model is going to do the classification correctly, right? Now, you do have the value you computed in training. You're going to compute some value at validation, and you're going to compare these two values against each other. If you had accuracy of 90% in your training, and after validation you against the 90%, then you could say that everything worked fine. My model was right. Right? The number of layers I said was correct. The width of every layer was correct. Everything is working fine. The model got validated. But if you do it in training and you see that after training, for training data you have 90% accuracy, but when you get the validation data, which was not inside your training loop, when you give it, now you are getting 60% accuracy. Then what does it mean? It means that it's working fine with the training set, but any new data is not doing as good as the data you had for training. So probably you need to do something on that. And this is what we do in hyperparameter tuning. Basically, maybe I need to add some more layers. Maybe I need to increase the width of a couple of layers and things like this. We're going to talk about this next lecture, okay? And once I got the new hyperparameters, like increase the width, again, I repeat the training, and then I do the validation to see whether they are meeting now or they are still very different, right? So I keep on doing this till I get roughly in the same range, right? This means that my model is getting validated now. And after doing that, you're going to use your last part of data, evaluation part, to just test your data for what we call a generalization. So I did the hyperparameter tuning. Now I want to get totally new data and see what is going on, right? If it's, again, totally different, this means that, again, my validation and hyperparameter tuning was not working fine, right? And then you essentially need to do more, okay? So just wanted to wrap up everything. So if you wanted to check more on that, you can check Goodfellow textbook. That is the best one with respect to deep learning. And Everything I told you here, it was a kind of like a super simplified version of what is happening really in practice. I do know that some of you might be interested to know more about that. So if you check Goodfellow textbook or other resources online, you're going to see those details. But we didn't want to just develop like algorithmic tools in this lecture. We wanted to get the idea how we do the training and how does the stochastic gradient descent work, and how we can evaluate everything. So I hope that it was clear enough. But if it was quite compact, I mean, deep learning, I cannot teach it in one lecture, right? So it could be a complete course. So that's because of that. So if you got any questions, just let me know. Next session, we're going to talk about generalization. So we're going to skip this stuff, assuming that they are working all fine, okay? Okay, so see you on next week.